and the short questions there. Okay, let me just. Okay. All right. So that is. So today we'll do the transmission line parameters. Transmission line, but what do we want to do? What are the 4 parameters in the transmission line?
Resistance, capacitance, conductance, resistance, capacitance, conductance, yes.
Okay, so a type of questions will be, is my voice clear to you? Is my voice clear?
Disconnected for some while, Doctor.
Disconnected. Okay, just for a while, yeah. But now it's clear or not?
Yes, now it's clear. Just now.
Okay, so it's not disconnecting. Okay, so that was the block. So it's okay. So the type of question, for example, in the midterm will be, how will you calculate the resistance? How will you determine the conductance? So what are the sort of, how do you calculate the conductance? So or what are the causes of conductance parameter? What does it cause? From where we get the conductance? Why do we have conductance as a parameter transmission line? Why? From where? What's the reason? We need to include in the resistance, for example. Okay, because of what? Because of what?
The conductance should be because of the insulation outside.
We say because of the leakage current through the insulation, maybe the leakage current. And okay, so the leakage current, corona also, because of the corona. So that's a leakage current. Leakage current, therefore, we can draw the capacitance or the inductance like this. The parameters, what we're talking about, are resistance, like this, resistance, and then conductance, like this, and then capacitance. Capacitor, we put it here like this, with a leakage with conductance. Okay, so this will be like this. And also from the other side will be the same thing, like this. And then capacitance. This is what we're talking about. This is what. So how do we, where we get, why, see, these are, we simply, we represent the reality with math. So we model the reality. We are modeling the reality. So what do we do when we model the reality? We have leakage current. Therefore, we draw this conductance. Okay. We have power losses. So why we get this resistance here? Because of the power losses. Therefore, we need to write resistance to present it. Otherwise, we cannot solve it. So we need to solve this one. Always we model the reality into circuits or mathematical equations. So we do mathematical equations to model the reality. Therefore, then we can solve it now. If we write the equations, we can solve it. So this is the whole idea. So why we get resistance, or why a resistance is a parameter in the transmission line? Because of the power loss. This is the answer. So these type of questions you need to understand. Why do we have inductance in the transmission line?
Because of the magnetic field.
Okay, so you need to elaborate on this, because of the magnetic field we have inductance. So when we say inductance, there is a magnetic field. But why do we have also in the inductance? So that's magnetic field. So we have what also? So you need to elaborate more. We have voltage drop on the transmission line. So the voltage at the sending end is not the same as the voltage at the receiving end. That's a voltage drop. Okay. Also because I X, and also we have a reactive power absorption on the transmission line, reactive power. So that's I square X. We have power loss, real power loss, and we have reactive power absorbed by the transmission line, reactive power. So that's I square X. Please. That's why we need to present it. We have charging current, as we can see later. We have charging current. Therefore, we need to put a capacitance. What capacitance is the charging current. So we have also current from the transmission line and the earth, from earth to the transmission line, and it depends. Yes, Muhammad.
Doctor, so when you say you need to elaborate more, for example, I should mention the I square X, yes?
Mention that we have voltage drop, I square X, yes, because that's why we included X.
Yes. Okay.
We have voltage drop, yes. Okay, so that's the type I would like you to focus on. So, okay, questions be it some. All right, so what we want to do today is to determine the inductance of the transmission lines. That's very important. The inductance will, as you can see, talk about maybe 2 lectures or so, just for the inductance by itself. But while the conductance we usually neglect, so if I asked you what parameters we can neglect from this, you see now these are the type of questions. What parameters? It's like an interview questions. So if you want to work as a power system engineer, these are the type of whether you understand or not, or you want to teach power, for example, in power lab. So what parameter can I neglect on these? If you want to neglect a parameter, what parameter?
The conductance.
The what?
The conductance.
Conductance, the G. Very good.
Yes.
So I can neglect the G, this one here. Okay, this is the conductance G. This is okay, but we never neglect the inductance. Okay. We can also neglect C, for example, this the capacitance. Okay, so part this is all is the C. We can also neglect sometimes in short transmission lines.
Doctor, why we can neglect the C?
C because it's compared to what is the losses and reactive power. This is why we can neglect for short transmission lines, because of the minor effect. All right, so okay, and when we talk about conductance, about inductance now, we talk about inductance. Therefore, it comes to your mind there is a magnetic field. Where would we get this magnetic field? Because we have a number of wires close to each other, or maybe just 2 wires. So single phase. Single phase will have how many wires in the single phase? How many wires?
2 wires.
2 wires. Okay, so we have 2 wires. Because we have 2 wires, therefore we will have magnetic field between these 2 wires also. So when we have this, what you see here is the composite conductor. So this is one conductor, but stranded conductor, strands. So connects off a number of strands, Okay, as you can see on the picture here, a number of strands. And while we have a number of strands, why a conductor is a number of strands, as you can see on this picture here or on the composite conductor graph. Why? Yes, Yatami?
It's for the skin effect and the to avoid the low surface thing.
Okay, so that's all right. The surface magnetic field, but this for the skin effect, because the current will not because of the skin effect. And you know what is skin effect? The current tends to flow at the outer surface of the conductor. So if this is solid, the current will flow in here and will leave the solid. Therefore, we can make small solid conductors. Small solid conductors, as you can see, therefore the current will flow in here, there, everywhere. Okay. All right, so this is what you call the composite conductors. And because we have these, therefore we need to work on the inductance. Therefore we need to calculate the inductance. Now, suppose we have just a single phase diagram and each wire or each conductor has a number of subconductors as we saw earlier on the picture. Okay, so 1, 2, 3, 4, 5, N. And this is 1, 2, 3, 4, 5, M. Okay, so this is a single phase. We can, from this one here, we can have it like this. We can draw it like this. 1, 2, 3, 4, N. Okay, different spaces. It's not single. This one is here, one is there, one here, and also for the same other conductor, the return conductor. So we call it conductor Y. We have also 1 prime, 2 prime, until M, another subconductor. They are not equal in numbers of subconductors. Now talking about subconductors inside one conductor. So this is conductor X consists of a number of subconductors. Conductor Y also of M conductors. So the way to, or the formula to find the inductance is simply L of X. So the inductance of conductor X is 2 times 10 to the power of -7 natural log dxy dxx. We already had this before. That is the distance over the radius. We already discussed this in part 1. Distance over the radius. Here, the distance between x, y, so between each one to y, between 1 to 1 prime, 2 to 2 prime, 3 to 3 prime, and so on. 1 to 1 to 2 prime. So we can make it like this: dxy multiplication. Okay, k from 1 to n for each conductor. We multiply each conductor. We multiply by the distance between each conductor and x. So we call it dxy instead of just d. Remember that when we worked on a solid cylindrical conductor or just a single phase solid cylindrical conductor, we multiply the distance just d. Here we have geometric mean distance, dx, okay, called geometric mean distance, over the radius, dxx. So it's not r now. This is a geometric because we need the radius of the whole conductor here. This is one conductor. Conductor X consists of a number of conductors. So therefore we want to find the radius of this. So we call it the geometric mean radius. So we take the mean, geometric mean radius of the conductor, because this is only one conductor, as you can see. So the formula, we multiply them, as we will see later how we multiply. Okay. Now here you can see the xx. How many conductors here are n conductors? Therefore, we put n squared. So if we have 4, this will be to the power of 16. Okay. X squared is 16. So this will be 16. If we have 2 conductors only, there will be 4. This is n squared. So you will calculate how many conductors on this one. Therefore, you need to multiply n times 1 to 1 prime, 1 to 1 prime, and then 1 to 2 prime. These are the distance you will draw. Okay, from each conductor you will draw a line. These are the distances, and so on. And then another also, have not finished. Then from 2 also you will draw the same thing. From 1, 2 or 3 here, and then this is with a 1 here, and this is the 1 there, and from 3 and so on. You see, these are the multiplication. That's why we put them in this formula. All right, and that's why we put dxy. So dxy is not just between one point to another point. It is the geometric mean distance for each. Okay, so this is we call geometric mean distance, GMD as a short, and GMR is the geometric mean radius, dxx. That is for conductor X. For conductor Y, dxy, geometric mean distance, so between conductor to conductor, and dYy is the geometric mean radius of conductor Y. And here you will see here Henry per meter. So it does not depend, you will tell me, so it does not depend on the units of D. Units of D, this could be in feet, okay, feet. And also, this should also be in feet, no problem, feet, qadam. Feet over feet. This still will be Henry per meter. Henry per meter. It comes from here, from this one, because this one is from the permeability. As you remember in the first part, that we had the permeability 2 times 10 to the power of -7. That is the first part you review. How we determine the formula. So the units of 2 times 10 to the power of -7 is Henry per meter. Okay, so this is per conductor, as you can see, Henry per meter. Therefore, if how long is this one? 1 kilometer. Therefore, I need to multiply by 1,000 to get the inductance of conductor, the total conductance, and that is the conductance. After they multiply by 10,000, that's the conductance X that you put on the software that you, the Powerwall simulator. When you write the, so that is the conductance you for the conductor. Which conductance is L? This one here, L. So you add Lx and Ly. So you talk about, take care of about the inductance of the whole system. Okay, inductance of the conductor. So this is, we have 2 conductors, X and Y. And also we have inductance between, these are only because single phase, by the way, that's why, single phase. If we have 3 phase, therefore we need to calculate the inductance. And that's what engineers do. You need to calculate the inductance beforehand. Okay, that is offline. And then you put it on the software, or you put it on the system that you calculate the load flow. Okay. So you do offline calculation, because the length is the same. You will not change the length. So you know from Saeed to Al Wakra, for example. So you know the distance already. So that is, so you calculate these distances, and you already know whether it's 3 phase or single phase. Okay, so we don't have single phase, by the way, from Saeed to Al Wakra. Single phase is in your house, or something, or maybe in a small machine. Okay. Once you go for even the AC, for example, the air condition, once you go above 2.5 ton, for example, 3 ton or 4 ton in the mosque at the university, the big over 3 ton, for example, 3 ton AC air condition, then you need to 3 phase. Single phase will not be, otherwise the motor will shake like this. Okay. So you cannot supply more power. That's why we need 3 phase in machines, even in the air conditions that need more power. Air conditions like 3 megawatts, 3 ton, 3 ton. That's what you will see in the mosque, for example, this big one, and then some houses also. The houses that you need 3 phase if they have more that they have more than 2.5 ton. 2.5 is single phase. 2 is single phase. 1.5 ton is single phase until 2.5. If they go up higher, then they need to have a 3-phase system. And where they're connected just from the DP. Instead of having from the red, yellow, blue, they can connect the 3-phase red, yellow, blue from your DP 3-phase. And that is not a problem. So they can connect. They have swimming pool, for example, swimming pool. They want to heat the swimming pool. They need 3-phase. Because the heat for the heater. In the house, so we're talking about houses even. You need single phase. You need 3-phase. Okay, so now we understood how to calculate the inductance between conductors. As you can see here, we have conductor X. So you are not familiar now in conductor X. These are subconductors in one conductor. Okay, so we have all these are conductors. And we have conductor Y is only consists of 2 conductors. And the distance is 0.3 meter between these 2. And the distance between conductor is 2 meter between the last one and this one. 2 meters. So you need to know these distances. What do we want to find? We want to find the inductance. So this is a single phase. Conductor X consists of 3 conductors. Conductor Y consists of 2 conductors. Now we want to find the inductance. You see now, very simple here. What you will do now, what do we want to find? We want to find the geometric mean distance. So what you will do, D1, 1 prime, D1, 2 prime. That's it, because we have only 2 there. And then D2, 1 prime, D2, 2 prime. D3, 1, D3, 2. If you count them, 1, 2, 3, 4, 5, 6, there are 6. So that's why you will find these are 6. So this is the way you check your answer. This is the way you check your calculation before you give the answer. So you put 6 in here, therefore, because the end will be in meter or in centimeter, whatever is the units, or in feet. Okay, to the power 6. So this is a square 6. Okay, so 1, 1 prime, 2, 2 prime. Where do we get these? Is we get it from here. So therefore, you need to find the distance now. So from 1 to 1 prime, you will go all the way to here until 1 prime, then you stop. Therefore, what you will do here, 0.5 plus 1.5 here, plus 2, and then you stop. So from the center, okay? So this will be from 1 to 1 prime, you will plug in the number here. This will be 4 meters. And then from 1 to 2 prime, which is 1 to 2 prime, you will go all the way to 2 prime. So this will be 4.3 meter. You plug it in here and so on. So for you as an engineer, you look at the distance here. It's not just what is given and then I forgot to add this, or I forgot to add the 0.3. We cannot. This is straightforward, as you can see. So we want your focus. There is no room for mistakes like these. You are the one who will prepare the inductance of the system. Then the data entry person, the one who is just putting the data, may not be an engineer. Will be anyone who just putting the data X and Y, etc. And that's it. But you are the one who will need to calculate these. That's why you need to focus on these. To focus. So please, there is no room for mistakes like this. I forgot 1 prime, or I forgot 2 prime, or I forgot the distance. I did not see the distance. We don't want to hear stories on these. So you need to calculate. What are you calculating? 1 to 1 prime. Okay, therefore you need to calculate from 1, and this is the middle, okay, the center. to all the way to 1 prime. And then that's it. From 2, then you will go to what? To from 2, you will go all the way to 2. Okay. 2 to 2. Okay. 2 to 1, and so on. Okay. So that is the geometric mean distance. Now, before you go, and here also make sure that you understand what are these. This is n, and this is m is 2 prime. So n is 3, and that's why 3 square that you have it here. And this is 3 square. That's because we have 3 square, and here 2 times 3. That's why we have 6. 2 times 3. So you can write. You can understand this. Okay. So in the formula sheet, you will be given. You will be given the formula like this. But you need to understand what is this. Okay, this will not be given to you a square, etc. How to calculate in the exam. This is the formula you will use. So you need to know what is m. Okay. Or like this. These are the formula. These are the one. Maybe this one. You need to know what is mn. So n is the number of conductors. N conductor, number of conductors. Mn is we want to find the distance. How many conductors in conductor n? How many conductors in conductor, the other conductor? Okay, so this is the formula you will be given. So please understand the concept. And then what we do, okay, so therefore we can calculate the xx. The xx, now we are talking.
Doctor?
Yes.
What is the 0.03 in the example? This one Rx, or what is this? What it represents?
Represents the radius of each strand, the radius of this radius of each conductor, the radius, because we need this radius now. Okay, we need the radius. Okay, these are the radius of the conductor. It's 0.03 meter. This one here is the radius. 0.04 is the radius of each subconductor of this, and also of this. Okay, so Rx equals Ry. Sometimes we have different radius for each conductor. One is big, one is small in one conductor. But this is not in the transmission line. This is the theory behind this one. So it could be. So this is the way you calculate it. In reality, in transmission line, we don't have it like this. But this is to give you an idea. If we have 3-phase double circuit lines, therefore we need to calculate it like this. All right, so this is the radius in the terms of, okay. All right, so that is dxx, means that the geometric mean radius of conductor x. This is the whole thing. This is called conductor x. Geometric mean radius. How to calculate the geometric mean radius? We calculate it by d11, d12, d13, and so on. Okay. dxx. So let's say Abdullah.
What is D11? How much it will be?
What is D1? Very good question. Wallah, I like that you focus on it. D11 is the radius, which is Rx, that is the 0.03. The 0.04, for example, for D1 prime. Okay. So for this D11 is the radius of 1. You see, from 1 to 1. What? Is the radius. 1 to 1. This is the radius only for this. Which is what D11 will be. Will be 0.03. Will be this. 0.03 meters. D12, the distance between 1 and 2. So have this in mind. D11, D22, like this one here also. What's D22? Is the radius of, from 2 to 2. معناها the radius of conductor 2. The radius. Okay, 3, 3, the radius again. So now the radius, you have it there. Okay, so please focus on how, on these actually, the formula. You'll be given a formula, and therefore you need to deduct to write these. Okay, what is R11? What is, so instead of writing Rx, we write D11, D2. In this case here, D11 D equals D22 equals D33. So you don't need to calculate every, so it's only once. So much of the time you will spend it only on the calculation. So 1 1 equals 2 2 equals 3 3. Why? Because they have the same radius, 0.03. Also, this is only for what? For conductor X. Okay, that's what you did here for conductor X. Also, you do the same thing here for conductor Y. Therefore, you will have D1 prime, 1 prime. D2 prime, 2 prime, and so on. This is the conductor Y. Therefore, you will have it like this, as you can see. So these are D21, D22, you will make it, and DXX. So you find it like this, whatever. Okay, and again, the result you see now, after you calculate this, is LX. So this will be DXY. You will have 0.3 DXY. This is DXX. The last, this one, DXX. DYY or 0.9, which is this one, and DXY is 3.189. DXY equals DYX. The distance between conductor X, conductor Y is the same distance between conductor Y to the conductor X. You see, after all this one here, you will only calculate one of the distances, DXY. That's it. So you know now DYX. But DXX is different than DYY. Okay, so to save time, this is the way you will calculate it. DXY will be DYX. DXX, you need to find the geometric mean radius of conductor X. And again, this is very important to know the units Henry per meter. Per circuit, okay, no problem, per circuit. This is the total thing here you will put. And then you multiply it by the frequency 2 pi f, 2 pi f, to get the X. And this is the X that you put it on the circuit when you calculate the load flow or just circuit. That's what you put on the circuit. Okay, L, which is LXY. LX plus LY, you add them. That's the inductance. Multiply by 2 pi f, you will give you the reactance, which is X. Okay, so this is per conductor, and this is per circuit. You can, okay, note this in here. Per circuit means we have this single phase circuit, and when you write as a single line diagram on the circuit, you will put this. Okay, not X, not Y. It's per conductor. And then how many conductors we have? We have 2 conductors, because this is a single phase. Therefore, we add them. If we have 3 conductors, 3 phase, we add L, X, Ly, and Lz, for example. Or instead of X, Y, we call them A, B, C, or red, yellow, blue. Therefore, we add the inductance of the red phase, the inductance of the red, of the blue, and of the yellow. red, yellow, blue. So we add them together. Okay, if we want the complete, but we don't do this. We'll come to this one. But when we do single line diagram, we take only one phase. When we do single line diagram, we take one phase, and this one phase is representing the second, all the phases, because the phases are the same. They're only 120 degree. So we will come to the three phases. Now focus on the how we calculate composite conductors. We call it composite conductors. Okay, composite conductors. Composite conductors, it means that each conductor consists of subconductors. Each conductor, this is conductor X, consists of subconductors. Another, okay, or stranded. Now, a solid versus strands. This is a solid conductor like this. And this is a stranded conductor made of strands. In the solid conductor, remember this 0.7788 الحلوة دي اللي ركزنا عليها. Now it comes in again 0.7788. Do you know where we get this 0.7788? If you remember, we already explained this before. Where we get this number? Oh.
The natural logarithm.
The what? Given?
اللي هو ln, the natural logarithm, the natural log.
This was e to the power of -1/4. So when we calculate, so we from the identity. Okay. So and we call it r prime. You see now, so it's not the full radius. So it's not the full radius here, as you can see. And this is r prime because it's solid. Therefore, if it is solid conductor, we need, instead of calculating the radius or the geometric mean radius, we have only r prime. That's it. 0.7788 times r. But we do geometric mean radius if we have it stranded like this. So therefore, you need to read, when you read the problem, look at here. Is it solid copper conductor or strand conductor? If it's strand conductor, then it will not be r prime. You need to calculate the geometric mean radius. Sometimes we give it on the table, and this is an appendix A3. A3 is for conductor in your textbook. A3 is the conductor here. This is A3. Table A3 is for copper. Table A4 is for aluminum. Table A4 is for aluminum. Okay. So please, when you read, even if you're given copper and aluminum, don't just look at the table. Look at what is the title of the table here. This is table A3, characteristic of copper conductors. Please always, when you're given a sheet, look at the title of the sheet here. Any sheet, any table, look at the title. What do they talk about? What is it about? So not just to go there and find the data. So look at it here. These are copper conductors, as you can see. So therefore, it will be copper conductor, characteristic of copper conductors. But these are stranded. So therefore, I need to look at the geometric mean radius. Because why? Because this is a strand conductor. Yes, Muhammad.
I want to ask you, Doctor, why in the table they are not using SI units? I mean, they are using inches, not meters.
Good question here, because this is a US textbook. If you use a British textbook, you will see maybe not British. If we use any Asian, for example, if this is authored here in Qatar, we will use meter.
But still, for example, when we calculate the inductance, we put per meter or the resistance all per meter. But Here it's not in meters.
Here the distances are given, the distances.
Yes.
But the end will be per meter, yes, the end per meter. But if they wanted to calculate it per mile, then they need to do. So anyhow, because this is a US system, so they take it, even those, the ones they write, the standard, these about the American wire gauge, as you can see here, these are American standards. So that's why they use, to make it easy for the engineer in USA to read these charts, to read, because they work on feet, etc. And the end, it's okay, Henry per meter inductance, that's okay. Then it's just one conversion they need to do it to mile, for example, convert meter or kilometer into mile. Okay, 1.6. Okay, mile. Okay. All right.
Yeah.
So
but in the exam, you will give us the conversions, yes?
No, what conversion?
I mean, like meter to.
The exam could be given like this. This is the one here. This is why you need to know, to understand the units, the different units. So you deal with feet, or also you will deal with the meters. So there is no conversion. But what conversion in mile from kilometer to mile?
Like, for example, 1 foot is like 0.3048 meter, for example. If you ask for the answer in meters, if we need to make conversions.
Okay, I can give you these, no problem. But you don't need them if you are given, those are in feet, therefore feet over feet. So you don't, but it's okay. But sometimes we'll give you something that you will not use it. Okay, so we will give you, even if I give you maybe feet to meter, you don't need to convert feet into meter. So because these will be given feet over feet, so they will cancel. Okay, dxy over dxx. So dxy you calculate it in feet, for example, or inch, 5 here, and this one. These should have the same units. So what is given here? 5 feet. dxy, 5 feet. And dxx, so this is the geometric mean radius. So you go where? You go to the conductor, and then you will find it by 0.178. Where will I go? I will go for 0.12 strands. So I will go here. 4 and 0.12 strands. So this is the one. Okay. 4 and 12. So look at the 12 here. This is the 12. Okay. As you can see, the 12. So that's the where you will look at here. And this is what engineers are doing actually. You will deal with sheets data. So please understand how to read the data. So mostly engineers, they read with data. How do they interpret the data? It's already available. This is the manual. So you need to know what you're doing, what information you can deduct from here. And then you will look, and here this is 0.01750, you go up. This is written in what? In feet also. Okay, it's written geometric mean radius in feet at 60 hertz. Okay, in the assignment, I asked you to use this table here, whether 50 or 60, that's okay. Although it's given a 50, but it's okay. Because we don't have a table for the 50 hertz sheet. Okay.
So Doctor?
Yes.
So in any questions you'll give us, we'll assume the frequency to be 60 and not 50?
No, if I give you 50, you need to work on 50, okay? But if the table is given on 60, because it's not given in 50, the geometric mean radius is not given in 50. Okay, so therefore you will take it as 60. It's like the assignment, the note on the assignment, that you can use the data for the 50. Okay, so you will use this data for the 50. But if you're talking about this 50 hertz here, this is different now, different story. This is for the resistance. Okay, this is the resistance. So if you're asked, for example, find the resistance, you need to understand how to find the data from here. Okay, therefore you will go to the 50. So you will use this 50. But because we talk about the inductance, therefore it's not given in 50 hertz, it's given here as 60, the geometric mean radius. So geometric mean radius in feet. So they run this at 60 hertz, and then they calculated the geometric mean radius of this strand. So this is a conductor, and they have the test on there. So when they do the test, they do the calculation of the conductor, and it comes like this strands. So they have 12 strands, and this is the geometric mean radius of this conductor. Geometric mean radius. So it's the radius of the conductor. What's the distance between each 12 conductors, between each these? Okay, what we're talking about between these one. These are 12, for example. So the distance between each, they already calculated for you. Okay, you need to calculate 1 to 1 prime, 1 to 2, 1 to 3, 1 to 4, etc. Okay, and 2 to 1. So they need to calculate it, to calculate all the distances on this one, and then you get up, you will get the geometric mean radius. Okay, so 10:50 now. I will stop recording, but please register for the attendance now. Please register for the attendance.
Doctor?
Yes.
And on all cases, we have to find the total inductance. We should multiply by 2 in all cases.
To what?
And to find the L.
No, to find the L, you will calculate per conductor. Okay, per conductor, which is this one here, Lx or Ly. Okay, you calculate this Lx and Ly, for example. In our case here, Lx equals Ly. Why? Because they have the same. But on the previous one, it's different. Lx is different than Ly. This is Lx. That's what you need to calculate. Okay, Ly and Lx. And then if you're asked to find the total inductance, and that is the inductance that you put it on the circuit, by the way. Okay, sometimes we just per conductor, we ask you per conductor. Therefore, you need to find Lx and Ly. And if there is an Lz, for example, that's per conductor. If you are asked to add them, therefore you will add them, Lx plus Ly. Okay, Lx plus Ly, then you will get per circuit. And you add them, if that's your question. I don't know whether it's you multiply by 2, you mean you add them? Is that what your question?
Yes,
yes.
About?
Okay. Okay, so you add them. In 3-phase, we will see later in 3-phase what we do. Okay. In 3-phase. So this is per circuit. So that's the full circuit. Sometimes we do in just one phase, but that's another thing that we will talk about. Anyhow, I would like you to